So, good evening to all of you. Back to the third session of our research webinar. And today we have very good speaker, Nitin Sharma. First of all, I want to give his brief introduction. So, Nitin Sharma completed BSc from Desbandhu College, University of Delhi in 2018. Then he moved to MSc degree in organic chemistry from Delhi University. And he joined IIT Kanpur as a PhD scholar in 2020 under the guidance of Dr. D.S. Dethe. And moreover, he is my lab mate. So, Nitin, over to you. Please start your presentation.
Thank you, Subham, for this kind introduction. Am I audible?
Yes, you are audible.
First of all, we will see the learning outcomes of today's lecture. So we will learn about today the basic definition of total synthesis. Then we will see the retrosynthesis analysis of Taondiol. During our synthesis of this molecule, we see that during the synthesis of this molecule, we see the protection of ketone by ethylene glycol to form ketal, and then its deprotection. We will also compare the thermodynamically favorable and kinetically favorable formation of phenolate ion. We will see intramolecular aldol condensation as well as which is also known as Robinson angulation. And most important reaction we will see today is Lewis acid catalyzed Friedel-Crafts reaction to form 1,4 CC and CO bond formation. And we also learn about Wieland-Mischer ketone and how actually it helps to synthesize bigger molecules, and it acts as a starting material for total synthesis of many terpenoid-like molecules. So this is the structure of Taondiol molecule. So first of all, I will introduce this molecule to you. So this type of molecules are present in marine algae. Marine algae are microorganisms that act as potentially source of highly bioactive secondary metabolites possessing different skeletal structure and varied biological activities. Cypopodium zonal, it is a biological name of this marine algae. Cypopodium zonal is one such marine brown algae found abundantly in Western Caribbean Sea. Taondiol have similar structure to Cypopodium family, which have a benzopyrene moiety as the only skeleton exception. So this Taondiol molecule have a benzopyrene moiety at this position, and this Cypopodium family molecules have a benzofuran ring at this particular position. These marine alkaloids are known to show isotoxic and cytotoxic activities. So isotoxins are the compounds which are either toxic to fish or are toxins produced by fish. Cytotoxicity refers to the ability of a certain chemicals or mediator cells to destroy living cells. So now you know that what type of properties these type of molecules possess. The first total synthesis of this Taondiol was reported by Itara and his co-workers in 1973. The major drawback of their synthesis was the reaction yield is only 2% for the final key polyene cyclization step. So they have very low yield total synthesis of this Taondiol molecule. Therefore, a more efficient method for the total synthesis of Taondiol is desirable. And therefore, our group came forward in 2018 with this research article, which was published in Organic Letter, Enantioselective total synthesis and assignment of the absolute configuration of the meroterpenoid plus Taondiol. So we came up with a very efficient way of total synthesis of this Taondiol molecule. The main author of this molecule is Samarpita Mahapatra ma'am and Susanta Kumar Sao sir, and of course Professor Dethe. And this is the picture of our research group. The one in the middle with having pink shirt is our Professor Dethe sir, and he is Susanta Kumar Sao sir, and she is Samarpita ma'am. So I think it's enough introduction for this molecule. We will see now the retrosynthesis analysis of this molecule. As we see the structure of this molecule, we have a heterocyclic ring in between. So the first planning is to dissociate this CO bond here and generate this molecule 10. And this molecule 10 can be made from this molecule 11, which is a tricyclic alcohol having a allylic alcohol at this position, and from molecule 12. So plan was that we will use this molecule 11 and 12, and by using Friedel-Crafts coupling, we will synthesize this molecule 10, and on CO cyclization of this molecule 10, we will get this Taondiol molecule. Also, this molecule can be made from molecule 13. So we will see during our synthesis that how this ketonic group is changed to this allylic alcohol, and this also this molecule 13 is made from Wieland-Mischer ketone derivative. by using Robinson annulation. So this is the whole planning of the group, that they will proceed in this manner. By starting with Wieland Mischer ketone derivative, they first synthesize this molecule 11, and using this molecule 11 and 12, they will synthesize this molecule 10, and this on CO cyclization will give Taondiol molecule. So this is the whole planning. But during our synthesis, we face many problems, like as expected that this 11 and 12 does not give Friedel-Crafts coupling to give this molecule 10. So we will during our synthesis we will see what solution Professor Dethe and his co-workers do to give this Friedel-Crafts coupling. So first of all we will see the synthesis of this tricyclic molecule from Wieland Mischer ketone derivative. So this molecule having two ketonic group. One is alpha beta unsaturated ketone here, and one is isolated ketone group. So we have to add a ring at this side of this molecule. Therefore, we have to first protect this ketone group. So we use ethylene glycol and paratoluene sulfonic acid, which will protect this particular ketone only, because the electrophilicity at this carbonyl carbon is higher as compared to this carbonyl carbon, because it have alpha beta unsaturation. Therefore, by using ethylene glycol, we first protect this ketone and change this ketone into ketal. And next, we use potassium tributoxide base, which will abstract a proton from this particular site, because it preferably give thermodynamically more stable enolate ion. Suppose if we use LDA here, that will probably extract a proton from this site and give a kinetically favorable enolate ion. So therefore, we use potassium tributoxide, and that will give a thermodynamically more stable enolate ion. And then that enolate ion will attack on this 1-chloro-3 pentanone molecule and give us this molecule. And this molecule in the presence of potassium hydroxide base will give intramolecular aldol reaction and give us this molecule 15. This reaction is also known as Robinson annulation reaction. So we reach to molecule 15. Now the next target for us is to add a methyl group at this position, and also have to reduce this double bond. So we use lithium metal ion in liquid ammonia, that will generate first a lithium enolate here, and then that enolate will attack on methyl iodide, and we get this molecule 16. Now we have to reduce this ketone group into hydroxy group, and then have to protect that hydroxy using the benzyl bromide. So we use lithium aluminium hydride to reduce this ketone into hydroxy group, and then in the presence of sodium hydride base, we protect that hydroxy using benzyl bromide. Now the question is why we are getting this particular stereochemistry at this center. This is because when we draw this molecule 16 in chair form, we will see that the hydride ion coming from this lithium aluminium hydride will prefer to attack from the below side of this molecule because of this methyl group. So therefore we are getting this particular stereochemistry in molecule 17. Now the left side of the work is done on this molecule. Now we have to work on the right side of this molecule. So first of all, we will deprotect our ketonic group in acidic condition, this ketal group change into ketone group. Now the next target is we have to reduce this double bond. To reduce this double bond, the first thing came in our mind that we will use any hydrogenation catalyst like H2PD charcoal, or any other catalyst like Adams catalyst. But that catalyst we cannot use here because of this OBN group. If we use those catalysts here, they will deprotect this OBN group. So we have to think of another method that will reduce this double bond. So here they comes with the Sandwich method of hydrogen atom transfer, which use manganese catalyst and phenylsilane. So this method use manganese catalyst and phenylsilane to reduce the double bond, and it is very efficient route for olefin reduction, and it also gives trans stereochemistry at the decaline ring junction. So by using this chemistry, we solve our two problems. The first, it does not affect this OBN group, and also give us trans stereochemistry at this decaline ring junction. Now this molecule 13, we have to add a methyl group at alpha position of this ketone group. Simply we use LDA in methyl iodide, and we will get this molecule 19. Again, why we are getting this particular stereochemistry in major form? Because if we draw this decaline junction in chair form, we will see that this enolate ion generated here will prefer to attack this methyl iodide from below side, because this methyl which is above will hinder the methyl iodide to come from the above side. That's why we are getting this particular stereochemistry at this alpha position of this carbonyl. Now this molecule 19, next challenge is to change this ketonic group into one carbon extra aldehyde, which is also alpha beta unsaturated. Now this molecule we use here this Nazoki-Yamamoto homologation reaction. So in this reaction, this ketonic group change into aldehyde with having one carbon extra in this way. So the most probable mechanism of this reaction is using carbine insertion reaction. So first of all, I think this base will abstract a hydrogen from this carbon, and then this molecule attack at this carbonyl carbon, and we get this intermediate molecule, and then this intermediate somehow with carbene insertion change into this intermediate, and then this intermediate change into this particular molecule 20. So the mechanism of this reaction is not given anywhere. So this is my assumption that this is how this reaction is proceeding. Now the molecule 20, we have to reduce this CHO group without affecting the alpha beta, this olefin. So we use Lucas reagent here and reduce this CHO into hydroxy group without affecting the double bond. So this is how we reach to our molecule 11. Now we will see the synthesis of the aromatic ring. The initial planning was that we will use this molecule 11 and this molecule 12, and using the Friedel-Crafts coupling generate our Taondiol molecule. But so the initial planning was that we will do a Lewis acid catalyzed Friedel-Crafts reaction between the diterpene moiety 11 and quinol 12 using boron trifluoride. But unfortunately, the coupling reaction did not happen as expected, and rather elimination of the allylic alcohol was observed as the only product. So what next? Then Professor Depthe and his co-workers think that if we increase the nucleophilicity at this carbon by introducing any electron donating group on this benzene ring, then this Friedel-Crafts reaction may occur on molecule 11. So it was anticipated that introduction of an extra hydroxy group onto the aromatic ring might enhance the nucleophilicity at the required carbon, and later deoxygenation of the extra hydroxy group would deliver the required pentacyclic Taondiol structure. The planning was that we will first introduce a hydroxy group on these benzene ring, and then after doing this Friedel-Crafts reaction, we will remove that hydroxy. So we start with molecule 11, trimethoxybenzene molecule, and with the help of Willsmere-Heck reaction, we introduce a aldehyde group at this position. And then this molecule 12 on reaction with aluminum chloride in dichloromethane will, this is aluminum chloride in dichloromethane is a very good demethylating agent. So it will demethylate the methoxy group on a benzene ring which have a ortho substituent to them. So it particularly demethylate this OMe and this OMe group into OH group, and we get this and also with the help of sodium cyanoborohydride we reduce this CHO into Me group. Now we generate this molecule 23. The only difference between molecule 23 and molecule 12 is that we have extra OH group at this position. These two OH now increase the nucleophilicity at this center, this carbon, and now this molecule 23 will give us the Friedel-Crafts reaction as expected. Now the molecule 11 and 23 when reacts, first give the CC Friedel-Crafts reaction and this CC bond formation, and then within less than 10 minutes CO bond formation took place, and we get this molecule 24 as expected. So Friedel-Crafts reaction of hydroxyquinol molecule 23 with diterpenoid molecule 11 in boron trifluoride directly furnish a pentacyclic meroterpenoid called 24, this one, by sequential CC and CO bond formation. Now in this intermediate we see that after formation of CC bond we have two OH group here. Now the question is which hydroxy goes into CO cyclization, because both are ortho to this CC bond formation. We are getting major product with this hydroxy only, and it was said that this hydrogen on this hydroxy group is involved in hydrogen bonding with the oxygen of the ortho methoxy group. Therefore we are getting this particular product as major product. And also after CO bond formation we are getting a trans chemistry here. This is because trans decalin system are more stable as compared to cis system. Now this 24 molecule we have a extra hydroxy group. Now the next target is to remove this hydroxy group from here. So we use so we change this hydroxy into triflate using triflic anhydride, and this OH is changed into OTF group. The OTF is a very good leaving group. Now this molecule 25 on palladium catalyzed reductive cleavage of this triflate will occur. So we use palladium catalyst, and that will cleave this OTF group, and we get this molecule 26. Now this molecule 26 we have to do the demethylation of this methoxy group here, and we have to change this into OH. The first thing came into our mind is that we will do the demethylation using the usual methods like using boron tribromide, boron trichloride in sodium hydride like base, which will give us demethylation of this compound, but this reaction does not occur here. So we have to think of any another method of demethylation. So we came up with this Yomoto's method. So demethylation upon implementing Yomoto's method by using this boron compound and triethyl silane to get silyl ether. So first of all, in first step, this particular boron compound and triethyl silane change this methoxy into silyl ether, and then did protection of the silyl ether with TBF to generate the desired demethylated product 27, and then we just deprotect using TBF and we get this OH group here. Now this 27 molecule, the last step is to deprotect this OBN group into we have to change this OBN into OH, and we use simply H2PD in ethanol, and this is how we synthesize our molecule Taondiol. I hope you like the chemistry used by our lab mates. Thank you.
So thank you so much, Nitin, for your opportunity presentation and your work, which you have drawn each and every structure very neat and clean. So now Nitin's webinar is open for question answers.
Sir, can you open please fifth slide?
Yes, sir.
Sir, next to this, after retrosynthesis. Yes. Sir, next please.
This one.
Yes, sir. Sir, in the Nozaki-Yamamoto homologation, what is the use of lithium chlorine tetraoxide, LiClO4?
Actually, I try to find the mechanism of this reaction. I also contacted to the main author of this article. Even he said that this reaction is going with carbine insertion step, and they actually don't know what actually happening in this step.
Looks like a Remertiman reaction, maybe.
Yes.
I think.
And these two intermediates. I have made these two intermediates with best of my knowledge. I don't know whether they are correct intermediate or not, but this reaction most probably proceeding in this manner.
Can you open next slide? Yes, sir. So in the second step, we have used AlCl3 CS2Cl2.
Yes.
It will reduce ortho-OMe group to meta-OMe group.
Yes, yes.
But it will not reduce to ortho-OMe group.
Actually, I read a research article for demethylation using aluminum chloride. They have shown in their research paper that the OMe group, which have a ortho substituent electron withdrawing group, will preferably go demethylation by this method. So I am assuming that as this CHO group is electron withdrawing and it is only affecting this ortho and para, it is showing electron deficiency at ortho and para position. That's why only this ortho and para to CHO is demethylated by this aluminum chloride.
Well, demethylation will be dependent upon the substituent attached to this ring. Demethylation will be affected by the substituent attached to this ring.
Yes. Because of
if
this. Yes.
Instead of CHO, only hydrogen will be present. Then
this aluminum chloride demethylation method does not work.
Okay.
Then we use the other demethylation reactions like using boron trichloride in sodium hydride. But that if we use that, then they will demethylate all the 3-methoxy group.
All these 3 OMEs group.
Yes.
Thank you.
Hello. Hi, Nitin, Prashant here. In second step, you are using sodium cyanoborohydride for the reduction of that aldehyde group. How it is converted into methyl? Actually, the sodium cyanoborohydride is basically for reduction of imine or in that pH if the pH is in acidic condition, if pH is in basic condition.
Yes. If pH is below 3, then it will reduce ketone or aldehyde and that into OH group.
Yeah, so it
Last
is.
night I am discussing the same thing with the Shubham, that how sodium cyanoborohydride is reducing the CHO into Me group.
Yeah.
And we have no idea actually why they use this reagent here to reduce the CHO. But I will ask to Professor Dethe. If he gave me answer, I will definitely give you the answer in our WhatsApp group.
Yeah. Okay. Thank you. And go to the please slide number 6.
Yes.
In 14 to 15, that is the last step in Robinson annulation type of. I mean, back now, that 14 to 15 step, the last step KOH. In there, there is two. This one, there is
Yes.
2 acidic proton here. So 1, 2, 3, 4, 5 membering is also preferable.
1,
No,
2,
sorry.
3, 4, 5, 6. So the
Oh, no,
proton.
no.
Yes.
Actually, I got it. Sorry, I thought there is one more carbon is there. Thank you.
Only 6-membered and 4-membered will be possible in this.
So, yeah. Thank you.
6-membered ring will form here.
6, yeah.
Any other question? Anyone?
Okay, Nitin. Hi, I'm Shah. So go to the last slide where you do the Wills-Meyer-Heck reaction.
Yes.
Not this one. Where Wills-Meyer-Heck reaction in try alcohol, that alcohol one. Last link
Okay.
is to it. That's this one.
Wait a minute. Yes.
So my question is, in at the compound number 21, there is a 3 centers is there on that group. So it is possible to generate CHO is there also.
Here, you are saying that we will get a CHO here.
Yes, all three. Only one position. You get selectively only one position CHO.
No, we will definitely get this product also in lower yield. But because of this OME, 2-ortho ME, I think this will be. That's why this is we get in lower yield.
I want to know what's the driving force to I get 22 is a maximum product. So what's the driving force behind it?
This electron donating group will increase the nucleophilicity at this particular carbon and this carbon, this 2-Me group. So attack will. Okay.
Okay. No, because actually why I say it, because there is a 3 OME group. So if 3 OME group present in any aromatic type of a thing, so it is sufficient to increase any electrons at any center of that ring, benzene ring. So we have also the 2 positions is present there.
Yes, but as here these 2Me are increasing the nucleophilicity at this and this carbon. That's why we will get these 2 products majorly. I think so.
No, as you can say, so where you written right now CHO, that one is the major product, but we are getting at 22 at why not?
This one is the major product because of this hindrance, because of this 2 OME group at this position.
Okay. No. Okay. You get it. After doing the reaction, you got that one is a major product.
Yes.
Okay. So how you separate it out? You have getting 3 different type of product, 1, 2, and 3. So how you separate it out? Both 3, because it's a very difficult task. If you see all 3 compounds, they are very similar to each other. Means that there is no any much difference.
So we use column chromatography for this. No.
Actually, if you can perform the column chromatography, you can see that because it is that much nearer, so you can't separate out in that method. Maybe SPLC is doing something else, but either GCMS. But you can't do that by the column chromatography. Whatever I know, you may check it out.
No, if you see that this and they are cancelling the polarity of this molecule, these 2 OME which are trans to each other, and if a CHO is here, we have different polarity of this molecule, and if CHO is at this position, we have different polarity of the molecule. So I think it is possible.
Actually, no. It's on the same ring, so it's not like that. Means that we haven't like that dipole moment.
Actually, if there is if there is 3 OME group now, so electron density is too much in benzene ring, so we can't differentiate between.
Separate it out like that. You are right.
RF value will almost same in major and minor product. Maybe it's possible.
Okay, then I don't know that how they separate these molecules. Sorry.
Okay. Okay. So no, it's okay. Okay, you will discuss in the next one. Go to another slide. Move ahead.
Here?
Yes. Wait. I see that. Yeah, one another molecule is not okay. So I think it's a very simple question, but we are showing that when we are using H2PD, sometimes it may reduce the benzene type of ring also. In some of cases, not all, but here it haven't doing this type of thing. So they took protection of something, or it is another method. So HDPDOS2.
H2PD will reduce the benzene ring in very extreme condition. We are doing this reaction at room temperature here. So it is not
because your electron donating group is also there. What OH minus OH. Okay.
No. At room temperature, it does not affect aromatic. It does not affect aromatic rings.
Okay. And another question, okay, you have on the 25 number compound. 25 number compound. So you say that we get Me here near to the oxygen. This oxygen 22.
Yes. Here. This one.
Type of oxygen. A 25 number compound.
Yes.
This one. Yes. Okay. This methyl. So you are saying that we are getting it. We are getting after doing 24. We are getting this 25 exclusively. So how you can get confirmed?
Okay. We are getting this particular stereochemistry at this ring junction in major form.
Okay. No, yeah. So that I want to know. So how you confirm it out? You get this one is a maximum, because I have done some of reaction. I can't confirm what's the stoichiometry of this.
Actually, when we see the XRD data of the molecule, then there's the we can see that which is the which molecule.
So if this means that you have a getting crystal of all of the compound, whatever you do the reactions. Every compound. No, you don't get it.
Not all of the crystal structure which have some kind of the complexity. Like if you proceed the reaction here, so we get this molecule. We have a two diasteromer of this molecule. One may be cis or second is trans. So when we check the crystal structure of the molecules, we find that this is the more closer to our product. So we separate
no.
it like this.
Because in your mixture, both of the product is present, na? Trans cis and trans both. You can't separate it out. First, you check both of them. So how you can say that? Means that it's my query. So how you can say that we have get this one or this one? Because if you right say, I will say you will do the NMR, but in the NMR also both of the present, both is present. So what was the idea? Because you read that paper, na? We haven't got it.
Actually, product ratio we can get here. You can get two product here. So one product is selectively higher than other one. So that is the major product for us. And if we do the crystal data of the molecule, we can confirm that the stereochemistry of this junction.
No. Yes, it is right. Whatever you say, it is right. So I just say that how you get confirmed, you get one is higher ratio and second one is lower ratio, because when we are performing the reaction in RB, we get mixture of both of them. So we can't say anything about that. Which one is a higher and which one is a lower. Either there is we just draw the mechanism, so we will say that this will happen. But we have some data also. You know my question. You understand my question? What I want to say?
Yes.
So that's I want to point out. That's all right, correct. Because when we do the chair form, it is a major product.
Okay, Vishal, when we get anything, so we will let you know about this.
Okay. Next one. Any other one? Okay. Thank you.
Thank you, Vishal.
There's a little bit doubt from my side also. Please go to slide number 6.
Yes.
So I have a doubt like 16 to 17 compound. So we have taken lithium aluminum hydride. And if we talk about the reactivity of the molecule, because we have simple ketone here. So if we perform like a sodium borohydride and other reducing agent as compared to lithium aluminum hydride, so that reaction will work very well, and also we can control the reactivity of the molecule. So means if you use here lithium aluminum hydride, so what is the how can you control the reactivity, because it is very odorous to handle this one.
As we are changing this ketone directly into OH, so lithium aluminum hydride Yes. So
Because
suppose
it is reduced to ketone to alcohol, so that is good thing. But what kind of equivalence you can maintain here if you say the reaction condition? Actually, this
so
question
you are
asked
saying
me
why
to
don't
answer interview. One
okay
supervisor asked me to perform the suppose you want to reduce the aldehyde and ketone by the lithium aluminum hydride. So how can you say that? How can you handle the reaction also? Because it's the same question I have found here. Because we have sodium borohydrate and other reducing agents also.
yes. So the question is that how we will handle this lithium aluminum hydride in this reaction.
Yes, sir. Because one equivalent of the LAX reduce 4 molecule of the aldehyde of ketone.
Yes.
So generally, what we can do, we can take only 1.4, and 0.25 equivalent of this lithium aluminum hydride.
Okay, we take 1/4 equivalent of the starting material. You are saying
because there are the four hydride atom is there, which can if we take one equivalent of LAS, that will selectively reduce to 4 ketones or 4 aldehyde.
yes. I got
So
what you are saying.
So we can use only 1/4 equivalence of this LAS.
Okay, we will use 1/4 of the equivalent of this lithium aluminum hydride. I got what you are saying. Thank you.
Subham. Okay. It's okay when we have a lot of ketonic compound is there. So in this compound, 16 compound. So if let's assume that we are not using 1/4 equivalent of that. We are using one equivalent. So what will happen?
So if we take, so the question is that if we take one equivalent of this one, so because this reactivity is very much high of this molecule, so it will reduce to this one, but it can reduce to four times of this this ketone.
No, actually, you are right. You are right. Whatever you say, you are right. But in this reaction, if we are using the lithium aluminum hydride in one equivalent, only it will happen. Our reagent gets waste, but nothing will happen because we haven't any other ketone or any something else that can be reduced. So here we can use.
You can use that. So I said, my question was that what is the condition if we take this molecule to equivalence, because when we perform the reaction, we check the equivalency of the each of every reagent. So
Yes, you are right. On that state, we mean that when if we want to perform some reaction, we just use expected. We don't waste some reagent or some compound. So if we are using 1/4 equivalent, that's enough. Because it's a science, if we are using more than that, what happens? Nothing will happen here. But if any ketone or ester compound will present here, that will also reduce. So that one harm. Okay.
Another question from audience side.
Hello.
Another question. Okay. So thank you for your presentation, and each and everything was very nice. And I hope we will meet the next seminar, which will be held. The next presentation will be presented by Saifali, and when it will be held, we will let you know. Thank you, everyone.
Thank you, everyone.
Everybody can leave.